Section 9.2, Regression. When we talk about regression, this is really a continuation of correlation. Correlation shows what direction the data is going, and X in relation to Y, one relation to the other. With regression, we're going more detailed with the correlation. And what we're trying to do is determine an equation so we can forecast where future data is or where data may sit between certain points to get an idea. If you remember from algebra, all we need is 2 points to determine an algebraic equation. And what we have, we got to find the slope of the line. We find our 2 points relegated by x1 and y1, a second point x2 and y2. And we find the slope of the line by subtracting y2 minus y1 over x2 minus x1. And then we have our equation. Our y equals our mx, m being the slope we've determined, plus b, which is the y-intercept. Let's go through this right here. I've got a point, first point 4, 8. So this would be right here. And it's on this line right here. Here's 1 point right here. Pretend we don't have the line yet. Second point is 12, 16. Here's 12. Here's 16. And I actually determine what the equation is for this line. Now, as you see here, my slope, which is my m, is y2 minus y1. 16 minus 8, which is right here, which gives me 8. And then x2 minus x1. Whatever order we go, we have to make sure we're consistent. In fact, we subtract the second from the first on the y. We have to make sure we subtract the second from the first on the x. 12 minus 4 right here. And that's also 8. 8 over 8 is 1. So my slope is 1. Now all I have to do is put in either point. Now put in 12, 16. Y equals mx plus b. And y equals mx plus b. And I'll use 12 and 16. So my y is my 16 here. My x is my 12. My slope is 1. So 16 equals 1 times 12 plus b. And that means 16 equals 12 plus b. B is simply 4. And that is, if I put in x for 0, it's right here. It is where it intercepts. That is the y-intercept at 0, 4. So I have my equation here for these 2 points. And so what I have here is a set of data I'm graphed along an x-axis and a y-axis. And want to see there's some kind of relation. And just looking at this roughly, you can see there is some kind of positive correlation. I'm drawing a line that goes up and to the right. But can we determine exactly what the equation is to predict this, where a point would be here or over here or even off the graph? We have a different graph up here. And what we're going to do is we're going to try to find a line that's the best fit. And the best fit doesn't mean it touches the most dots. It means it's the closest, the difference between every one of these is the closest it could be. This right here, you can see, is only off by a certain amount. This is off by a certain amount. This is off by a certain amount. It doesn't have to touch any of these points, but it has the shortest distance vertically on the y-axis between every point. And that's why it's the best fit. If you had a slide here and you had a little line, a piece of string that went across it, which one gets it closest to every possible line? Now we can do this manually, take some time and then measure the points and do our y2 minus y1 over x2 minus x1. Or we can use our correlation analysis as we've done before and go one step further and actually determine it algebraically. So as you see with a regression line, in this case, what we're really looking at is an algebraic equation, and we're going to determine the best fit. We've got a bunch of points here in this case, as we looked at before with the correlation of the GDP, gross domestic product of 10 countries, in terms of dollars, versus our CO2 emissions. And can we determine a line to predict where other points would be based on GDP? And that's what we're doing. If they make so much money, gross domestic product, what would roughly their CO2 emissions be? And we use this equation to find our slope right here, as I talked about before. Our m, which is our slope, and that's the equation, and then our y-intercept. And as you can see, we found all these components with the correlation. The sum of x, the sum of y, the sum of xy, sum of x squared, sum of y squared. So we just put these numbers in we found before to find our slope and our y-intercept. And this is our equation. Our equation for this, based on these 10 countries of their gross domestic product on the x-axis and their GDP and their CO2 output, is 199.5346x. That's the slope, plus 56.036. Put that in, we can find out, and I should say forecast and predict where other countries would be based on their GDP. Now there's another set of data we're looking at before. This is number of years someone's out of school versus their annual contribution into a retirement fund. And as before, I'm going to use the same data as before. I've got my sum of x, my sum of y, my sum of xy, my sum of x squared, my sum of y squared. I'm going to plug this in to find my slope. And I get a slope here of negative 0.37987, which means it's going to be a negative slope. It's down and to the right. And I look at this, the data is pointing that direction. Again, this is the best fit. In fact, it only touches 1 point, but it's the closest combined in terms of each individual point on the y-axis. So I find my find my slope, I find my y-intercept by plugging it into the equation, and I get an equation of negative 0.37987x plus 12.876. And that is my regression line. I could put in how long I've been out of school and predict for any time. Here's another one. This is Old Faithful, and this looks like it's pretty tight data if you look at how close it is to the actual line. I've summed it all up as before. I found my sum of x, my sum of y, sum of x times y, sum of x squared, sum of y squared. And I really just plug it in right here. I got a slope of 12.481. I got the y-intercept of negative 33.683, and that is my equation. Y equals 12.481x plus 33.683. And my x is how long it erupts. So I can predict by how long an eruption is by putting in the x, whether it's 1 minute, 2 minutes, 3 minutes, 3.8 minutes, any time here, and then predict how long it'll be between eruptions. And you can see this is pretty close. All these points are pretty consistent. That was a real strong correlation. You can see how predictable it is. And we can make other predictions. Now, we also did the one with the baseball players, and I'm going to show you an example of how to use this. And you can see we've got the salary in millions of dollars, total salary for all major league teams, all 30 teams, and then the average attendance on the y-axis. And I've put all my individual data in because I've summed it all up before. I did it before for correlation. I find my slope, I find my y-intercept, and this is the equation, 108.031x, which is the salary in millions. I multiply that number times the salary, and I got y-intercept to 16,583.79. And I can predict. Now, it's fairly loose. That's not the only predictor, but it shows that there is a positive correlation. The more salary someone makes, the more salary the team pays, the higher the attendance rate. So this shows a positive correlation, but there's obviously other factors involved. But again, we can predict this line. Now, I've created the same calculator as before. I want to show you a couple of things. This is actually all our data from the baseball team. I put it all back in here. And this is from before. You can see this is the correlation. And remember, we had a correlation when I calculated all this out. You have to make sure you put your number of points in. There was 30 in this case, 30 major league teams. And we got a correlation 0.7747. Well, I've also created a calculator that does all these calculations. right here. And you can see it calculates out my slope, which is 108.028, and my y-intercept, 16,586.812. Again, you just got to make sure you put in your x and y data right here. And then put in your input. And your data will automatically output, because I don't want you doing thousands of calculations to get what you can do in Excel here in a matter of minutes.